Welcome to the first video in the Class 14 series of class time lecture videos. Let's start with a little review. Let's start by considering the SN2 reaction of hydroxide with ethyl bromide. So here we have our hydroxide anion. We were drawing a double-headed arrow with the tail beginning at a lone pair of electrons on the oxygen and the head of the arrow pointing towards the carbon. That's where we're going to take these electrons and use them to form a bond. Well, if we do that, this carbon already has 4 bonds, so we need to break a bond. We'll break the carbon-bromine bond, and we'll give the 2 electrons to the bromine atom, so we'll kick it out as a leaving group as bromide, and in the process we generate ethanol. And if you recall, there was a good explanation for the preference for backside attack of our nucleophile onto the carbon electrophile in our SN2 reactions. That's because it accords with the molecular orbital theory. We're plugging a couple of electrons from our, non-bonding orbital on the oxygen atom into the back lobe of our anti-bonding molecular orbital between carbon and bromine, and that has the effect of breaking the carbon-bromine bond because there's a node here. These lobes cannot overlap, and we formed an oxygen-carbon bond in the process. This is the transition state. There are certain parameters that we need to consider for the SN2 reaction. They include electrophile structure, the nucleophile, both its structure and its strength, the leaving group, and the solvent can play an important role in these substitution reactions. So let's start by considering the electrophile structure. We may also revisit some of these points in future class times. I don't know if we'll get through all of the points exhaustively in this one class time series of videos. So for electrophile structure, branching at or near the reacting carbon decreases the SN2 reaction rate because it increases the activation energy. And this should be something that's fairly evident because kinetics depends on activation energy, and if you decrease the reaction rate, you must have increased the activation energy for that reaction. So let's look at iodide attacking some alkyl bromide. Bromides are a leaving group, iodides are nucleophile, and we get our substituted alkyl halide, in this case an alkyl iodide. Let's look at how that depends on what R is. What is the alkyl group? Well, we're going to say methyl. If R is methyl, we're going to set that as a benchmark. We'll call the relative rate for that reaction 1. If R is methyl, our reaction goes 145 times faster. Of course, the methyl group is easier for the iodide to negotiate because it only has 3 hydrogens hanging off of it than the ethyl group, which has 2 hydrogens and a methyl group hanging off of our reactive carbon electrophilic center. If we extend this further and we go to propyl, maybe we only decrease the reaction rate by, a small amount. So in terms of a relative rate, we're at 0.8. What if we're isopropyl? Now, we're substituting another one of these hydrogens for a methyl group. When we went from methyl to ethyl, we substituted a hydrogen for a methyl group. We decreased our reaction rate a couple-fold. Now we'll substitute another hydrogen on that reactive carbon center for a methyl group, and we'll get the isopropyl group. Wow, our reaction rate went down to 0.0078. What if we had this, branching further away from our reactive carbon center? So what if we have an isobutyl group? Our reactive carbon center is a primary carbon, and now it's the carbon adjacent to that is tertiary. It's well branched. Well, our reaction rate is 0.03. course, we could continue branching our carbon adjacent to the reactive carbon center. Here's a neopentyl. Wow, 1.3 times 10 to the negative fifth. So we won't see neopentyl type groups in SN2 reactions. How about if we fully branch our reactive carbon center? What if it's a tert-butyl group? Well, our SN2 reaction rate is essentially zero, so we will not see tertiary carbons as carbon electrophiles in the SN2 reaction. So a little on naming. Our reactive carbon center that's bonded to our halide or leaving group is the alpha carbon. A carbon adjacent to that is a beta carbon. A carbon adjacent to that is gamma, and so on and so forth. Obviously, beta branching, the ethyl to propyl slows the SN2 reaction. And the more beta branching you have, the slower it gets. Of course, alpha branching is a much more steep sort of slowdown experienced in rate, as you saw going from ethyl to isopropyl to tert-butyl in terms of what happened to the rate. So we will continue forward. We still have a few minutes on this video. Neopentyl groups rarely participate in SN2 reactions. For the purposes of this class, we rule them out. Tert-butyl groups aren't seen in SN2 reactions. In fact, no tertiary alkyl halides will be considered to undergo SN2 reaction mechanisms for the purposes of our class. Most primary alkyl halides undergo SN2 reactions readily, except of course for neopentyl groups, which we saw had a very low rate. And sterics plays a crucial role in the structure of the electrophile. So let's look at our minimum steric hindrance case. Here we have iodide approaching the methyl carbon of methyl bromide. We're going to break the carbon-bromine bond. That was our minimum steric hindrance case. What if now we have ethyl bromide? Well, in the most stable staggered conformation of our ethyl bromide, as our iodide comes into the backside of the carbon, it looks like it's going to be eclipsing the hydrogen on the methyl group in the back. And so that increased activation energy relative to methyl, since we have a beta carbon hydrogen that lies in the same plane as the incoming iodide nucleophile, that raises the activation energy and it slows the reaction rate. And that's why, you know, iodide attacking methyl bromide is 145 times faster than iodide attacking ethyl bromide. What if we branched further, beta branching, right? For our most stable staggered conformation of propyl bromide, now we would have a methyl group eclipsing our incoming iodide, right? Because the anti-conformation where the methyl group is directly opposite the bromine group would be our most stable staggered conformation. There's too much steric hindrance, believe it or not, in this transition state between the methyl group that eclipses the incoming iodide nucleophile. We have to change our staggered conformation of our 1-bromopropane in order for this reaction to happen. And that decreases the reaction rate a little bit more, but it makes it possible. We have to go to the gauche conformation, where the methyl group is gauche to the bromine. And now our iodide eclipses a hydrogen, so that's not so bad on the beta carbon. We've seen that before, but we still had to put this in an energetically less stable staggered conformation, and that adds to the activation energy, and that's why 1-bromopropane proceeds a little slower as on electrophile in the SN2 reaction than 1-bromoethane. So the additional gauche, methyl, and bromine interactions raises the activation energy relative to just ethyl, and this slows the reaction rate. Must have killed a bug in my notes here. Anyways, I'll go ahead and end this video because it's 10 minutes now and we're getting kind of tired and non-focused. How about cyclic alkanes? Wow, bromocyclopropane is very slow, relative rate of 10 to the minus 4th. Bromocyclobutane is pretty slow, relative rate of 8 times 10 to the negative 3rd, compared to what? Compared to bromocyclopentane as our electrophile. We give that a relative rate of 1. And that's actually faster than attacking bromocyclohexane as an electrophile. That's 10 to the minus 2. And that's because our nucleophile has to interact with other axial hydrogens as it approaches the backside of the carbon, trying to displace the leaving group. So cyclohexanes are kind of slower to react. They do react, it's just a slow rate. Our bromocyclopentane is our fastest cyclic reacting electrophile. It's on par with isopropyl bromide, which we give a relative rate of 1, 2. So interaction with axial hydrogens slows the rate. And we'll pick up here on the next video.